We will often simplify our problems by looking at idealized systems, and that one of the most common idealized systems that we look at is an ideal gas. So let's answer the question, what is an ideal gas? If we have a system containing gas particles, in general we know that those gas particles take up some volume in the container. In addition, those gas particles interact with one another. However, to make our problem simpler, we're going to consider the case where there are no interactions between gas particles, which means that all collisions between gas particles are elastic collisions. And indeed, all collisions between the boundary, the walls of the container, and the gas particle will also be elastic collisions. In addition, we're going to consider that our gas particles take up no volume. So the volume of empty space in the container is equal to the volume of the container. This considerably simplifies our problem, and we'll find that in this case, the pressure, volume, temperature, and number of moles follow this equation of state. Let's take a look at how this simplified view of gas particles leads to the equation of state for an ideal gas. So consider a particle of gas in a container, and it's going to be moving in that container and bouncing off the walls of the container. So let's imagine the gas particle hitting this face of the container. When it does, it undergoes an elastic collision, heads back towards the opposite side, undergoes another elastic collision, and heads back towards this right-hand side of our container. Let's look at the force with which a particle hits this area. Because if we know the force that the particle hits this area with, we can calculate the pressure due to that collision. If we add up the force of all collisions from all gas particles, then we get the pressure exerted on the walls of the container. So mathematically, we can describe the pressure as the number of collisions, number of gas particles colliding, times the average force per particle divided by the area over which that force is applied. The force, remember, is the mass times the acceleration. And acceleration is how fast the velocity changes with time. So delta V over delta T. Let's imagine one round trip of our test particle. So if it starts at this right-hand face, moves towards the left-hand face, it will be going at a velocity minus Vx. It'll undergo an elastic collision with the left-hand face and move back towards the right-hand face with a velocity Vx. So the final velocity is Vx, the initial velocity is minus Vx, and so final minus initial gives us a total change in velocity of 2Vx. The time it takes to make that round trip is the distance traveled divided by the velocity at which it was traveling. The distance that it traveled was 2 times the length of the blocks, or 2a. Thus, delta Vx over delta t is equal to Vx squared divided by a. And now we're ready to put this all together into our pressure equation. So the pressure is the number of collisions, number of particles, n, times the average force per particle. The average force is the mass times the acceleration, or mass times delta V over delta x. So it's the mass times the average square velocity divided by a, that's the force, divided by the area over which that force occurs. Notice that the length of the box times the cross-sectional area is just the volume of the box. So I can write A times the area of one side as the volume of the box. Now, the velocity in the x direction is only one possible direction, so I can go in Vy, Vz, and Vx. The average velocity in each direction is the same because it doesn't matter which direction my gas particle is traveling. So the average square velocity, if I divide that by a third, one for each direction that the particle could be traveling, the average velocity in the x direction is 1/3 of the total average velocity in any direction. We can use our classical average value theorem to show that the average square velocity is 3 RT over the molar mass. Recall also that the number of particles times the mass per particle is the same as the number of moles times the mass per mole. Making these substitutions into our equations for the pressure gives us the following equation. The molar mass cancels, and finally the pressure is equal to the number of moles times the gas constant times T divided by V, which you know as the ideal gas equation of state.